Good morning, everyone. We're just going to give it another 3 to 5 minutes to see that we admit everybody, and then we're going to get started. Good morning, and thank you, everybody, for joining us today. I'm going to introduce our researchers and our presenters for today. Leander, if you can just turn your camera on, and Sam. Leander is a senior researcher at the CSIR. She has over 13 years of experience in water quality, microbiology, and bioremediation, and her work focuses on advancing nature-based solutions to improve water security, with an emphasis on translating scientific research into practical, context-responsive interventions. She was recognized as one of Mail and Guardian's 200 Young South Africans in 2023 in the environmental category, and as a JCI 10 Outstanding Young Persons awardee. Leander is also committed to mentoring emerging scientists and contributing to capacity development within the water sector. She works with Samantha McCullough Jones, who on this project and a senior water researcher who focuses on the social aspect of this project and is working with communication and information dissemination. They'll be presenting their work on algae-based phycoremediation as a low-energy, nature-based solution for improving water quality within rehabilitation and land use systems. Drawing on evidence from South African pilot sites, the presentation will demonstrate how passive algal systems can support the treatment of nutrient-rich and organic effluents with potential applications in mining, rehabilitation, and agriculture. It will further highlight practical considerations for implementation and opportunities to integrate these approaches into landscape restoration and sustainable water management strategies. So without further ado, I'm going to hand over to Sam and Leander. Sam, I think you're going to get started for us.
Yes, thank you, Abigail. Leander, will you just flight the presentation, please? Sure.
Hey, thank you. So thank you very much, Avi, for the introduction. So morning, everyone. So today, Leander and I are here to just tell you about some of the work we've been doing around algae-based bioremediation and how we are moving towards industrial effluent application. Okay, next slide. So this work is part of the SIIP program, which is the sorry. It's the Strategic Bioinnovation Program, which is funded by DSTI and is led by CSIR. It's focused on advancing bio-based innovation in industrial sectors and bridging research, pilot validation, and industry uptake. In addition, it's about supporting scalable, local relevant solutions, and the SIIP program exists to move promising bio-based innovations from research into real industrial application through structured partnerships. So the SIIP program is structured around a number of pathways, and these are vertical technology pillars supported by cross-cutting mechanisms that de-risk innovation for industry. So as you can see, we have our vertical interventions, which include integrated biorefineries, bioconversion and manufacturing, microbial bioprospecting, industrial biocatalysts, as well as bioremediation technologies. And the horizontal interventions include innovation support and human capability development, upscaling and demonstrating facilities, inbound technology transfer and bio-entrepreneurship, as well as evidence-based policy briefs. I'm going to now hand over to Leander, who is the microbiologist that is working for CSIR based on this work. Thank you, Leander.
Sure. Good morning, everyone. I'm just going to talk us through some of the work that we've done, looking at algal bioremediation or phycoremediation, and we're going to look at it from where we started, from the domestic effluent treatment perspective, and the applications or the current work we are doing for industrial application. So the background is basically with all the compounding issues with South Africa's water treatment challenges, infrastructure, load shedding, day zero, and so forth. Um, with such major challenges, we need equally robust solutions that are, feasible, environmentally feasible, and ultimately feasible from a cost perspective, and are as efficient. So this brings us to the concept of phycoremediation. This basically, in our instance, the idea is the use of algal, microalgae or algal species to remediate or remove pollutants. In our context, it's the use of a chlorella co-culture that we've started working with about, I think it's about almost 10 years now. And it's basically low energy aerobic, no mechanical aeration required. And from that, we've seen an improvement in water quality, in the diversity, ecosystem diversity, and the potential for emerging contaminant removal. So the work started in the lab. We started growing the co-cultures together. We started upscaling them in the lab, and we tested them at a lab scale against sewage water. And we found that there was quite a good reduction of nitrates and phosphates. And that led to us actually piloting the algal treatment at one of the wastewater treatment works in Watetema wastewater treatment works in the Sekhukhune district. And from there, you can see how, if we follow the clockwise diagram on the right, we upscale the algae, we had the bioreactors piloted at the wastewater treatment works, and the greening is basically the color when the ponds are dominated by the algal species. We've also tried to start the biomass harvesting and valorization, and this is just an example of what the algae look like when they're concentrated after they've been harvested from the ponds. And we've also supplied the municipalities that we've worked with a training manual. The diagram on the right just shows how they can actually visually be able to tell when the algae are ready for dosing into the ponds and when the algae require nutrients, and how they're supposed to respond to that. So the idea is that low skill operators can make use of this. So you don't need to be, have any sophisticated knowledge. It's an easy to follow training manual to enable municipalities to upscale the algal cultures that we supply to them to be able to maintain the treatment at the pilots, at the different pilot plants. So we've piloted the algal treatment at Mototema Wastewater Treatment Works. That was our very first pilot. We've also worked with Bitterfontein in the Matikama district. We've also done some feasibility testing and one pilot at Unimar in Malawi through a combined SADC project that we embarked on a few years ago. And then we've also piloted the treatment at Brandwacht Wastewater Treatment Works in Mossel Bay. That is our longest ongoing partnership. We piloted the technology in 2017, and we've been monitoring and basically collaborating with the municipality since then up until now. So this is just a graphical layout of the Mossel Bay wastewater treatment plant. The algae are dosed in the third pond, the aerobic pond, so from pond 3 to pond 7. In pond 1 and 2, it is anaerobic ponds, so we only introduce the algae from pond 3, and we look at the change in the water quality and improvements in parameters from the initial dosing pond, or from the initial inlet, the dosing, and the final pond 7. So on the right is just a depiction. We were actually at the site in February this year, and this is just to show what it would look like when the algal treatment is piloted. It's literally having bioreactors there, having infrastructure to be able to dose into the specific ponds. So it's not a high cost implementation or application, and it is normally self-sustaining in the natural environment. And within the work that we've been doing, we've also tried to get some communication and dissemination work done, basically trying to increase the knowledge and awareness on nature-based solutions. This is within the domestic effluent treatment space. And we actually had a practical with NMU students in the Mossel Bay plant, just for them to have a look at how the water quality improves and the ecosystem diversity improves from the initial introduction of the algal species to the final pond effluent. So we actually have a little video clip that I'm going to play, and I hope it's I hope it's informative.
Some assistance maybe with the technical side, Leon, to just check the screen share. You might just need to change to the other tab.
Oh, I apologize. Let me just stop the video. Okay. Sorry, the video had started and I
And if it's not working, let's just put the link in for people to watch in their own time afterwards.
Okay, yeah, I
I'm
think
struggling.
okay, there we are. Got it. Okay, got it. Start it again.
I'm not getting any sound.
Is there no sound?
No, there's no sound.
Is there no sound? Okay. Okay, I think then in that case, I'll just drop the link. Sorry about that. Okay, so let me go back to the presentation. Okay, so I'm sorry about the sound there. I was hoping to share a video just to show, on a much, on a more interactive interface what it was that we did there. But it was basically a practical with students from NMU and some interviews with the municipality and basically their experience of the passive treatment and the water quality improvements that they've observed. It was just a nice little clip, but I will share the link in the chat box. So that is what we've been doing just to increase awareness and knowledge dissemination in the nature-based solutions space. Okay. And if we look over the years since 2017, since the implementation of the treatment, and 2025, comparing some data from our July 2025 sampling, we can see that over the years, there's been a consistent and significant continued increase in water quality improvement. So if we look at the final output pond 7 in 2017, and we compare the inlet and the outlet ponds in 2025, our winter sampling, we can still see quite a significant reduction in nitrogen, chemical oxygen demand, and some phosphorus reduction and a major reduction in turbidity. So this is just for us to look at how how the algae are still performing, or the expected performance from the algae over the years, having given the municipality the initial tools for them to maintain the algal cultures and how to dose. So we normally just send them 25 liters of the cultures just to ensure that the correct strains are still dominating, and then they maintain them and continue dosing as needed in the ponds. So this was just a confirmation that the algae are still performing consistently as we would expect, just looking at some of the major parameters. So over the years, in terms of the efficiency, the other added parameters we've looked at is the ability of the algae to remove or sequestrate pathogens. And we found that since the pilots in 2017 up until now, there's been at least a log 4 reduction over the 8 years. And with the added assessment into the biodiversity of the ponds, we found that there've been increase in bioindicators such as Daphnia, which are very good indicators for water quality. So we find that the overall ecosystem diversity increases, and we get sensitive bioindicators such as Daphnia also increasing as the algae continue to dominate and treat the ponds, especially in the final effluent pond 7. So we've also looked at the potential of algae to remove emerging contaminants. This was a study we also did at Brandvacht from the effluent in Brandvacht, and we looked at the ability, the change in the antimicrobial resistance profiles prior to treatment from the algae and after treatment by the algae. And we also looked at the most persistent antibiotics. So sulfamethoxazole, for example, has been identified as one of the persistent antibiotics in the environment. And so we conducted a study, a lab scale study, looking at the ability then of the algae, the chlorella co-culture, to actually remove or transform selected antibiotics. So we looked at amoxicillin, sulfamethoxazole, clarithromycin, trimethoprim, and afloxacin. And just based on that study that we conducted, we found that the algae were actually able to reduce sulfamethoxazole and afloxacin over a 10-day period. Looking at lower concentrations, was about 77.3% reduction or removal of sulfamethoxazole, and 46.5% at the higher 100 parts per billion concentrations. Similarly, for afloxacin, there was a 43.5% reduction of the lower concentrations, which is 10 parts per billion, and a 55.1% reduction for the 100 parts per billion. So that gave us an indication that the algae do have a propensity then to remediate or remove emerging contaminants. So we then looked at the application in industry. So we were able to obtain effluents from two wineries, local wineries, and one sample from the paper and pulp industry. So this just speaks to the different profiles of the effluents that we tested and the pH range. So from the winery effluents, we received effluents that were circumneutral, and then the paper and pulp was actually very low pH, very high sulfates, and it was also dark, meaning that that would have an impact on light penetration for, photosynthetic organisms like the algae. And these were just some of our findings. So we had samples from winery A, winery B, and a paper and pulp sample, of which the treatment process in winery A was going through a bioreactor and nanobubbler, and the final effluent was released into the irrigation dam. So we sampled prior to the samples actually going into the bioreactor, and we also sampled what was released at the irrigation dam. For winery B, they follow a process of producing effluent and then liming it to increase the pH, then combining that effluent with some domestic effluent, so some sewage, and then treating through a reed bed. And then they've got some kind of a spiritual aeration pond, so some yin-yang linked treatments to their effluents. So we sampled the limed effluent, the combined effluent that was combined with the domestic effluent, and then what was the final effluent after the reed bed treatment. From the paper and pulp sample, we were basically given effluent that is discharged in very large volumes, on a regular basis. So there's not much retention time. But the idea was to basically explore the algal compatibility with this kind of effluent that is, with that kind of profile effluent, to just see whether it would be a fit or whether it could be applicable in that space. So we looked at the chlorophyll production. Chlorophyll A is basically a good indicator or reference indicator of algal growth or proliferation. And then we also looked at the optical density. The optical density then complements the chlorophyll production measurements by looking at the biomass. So we look at turbidity to actually indicate whether there is biomass increase of the algal cells. So basically what we found, we are discussing the results or the preliminary finding from winery B, and we found that there was an increase in chlorophyll A in the limed effluent, and there was a slight dip, which could be expected because the algae basically have a 3 to 7 day they have a lag of about 3 to 7 days, and then they start reaching the exponential phase. And some of the samples, like the reed bed treated sample, seem to create a decline after day 3 in terms of the chlorophyll production, and similar effect is also noted in terms of the biomass. So it seemed to be that the algae were able to proliferate or continue growing in the limed effluent and the combined effluent, which is not surprising considering that we have applied algal treatment in the domestic space. So the combined effluent, which is the limed effluent with the sewage or domestic effluent, would be a good substrate for the algae to grow on. We then also looked at the reduction of coliforms, or E. coli specifically, as our pathogen indicator. And within this specific winery effluents, we found that by day 3, or by day 7, for the most part, in the limed and combined effluent, there had been a total eradication of coliforms from between log 6 and log up to log 6, basically reduction. In the limed effluent, that was not observed, and we will talk into that in a little bit. But in addition to that, we also wanted to have an idea of what compounds are being removed. So we just did a basic screening using nuclear magnetic resonance that basically identifies compounds, simply put, according to how and where they peak on the spectrum. And we just wanted to know, apart from what we are seeing, the algae growing, the biomass increasing or decreasing, and the sequestration or the removal of pathogens, is there any transformation of compounds? Is there any other additional bioremediation occurring at that level and at a chemical level? So we found that I've spoken a bit to this, but the algal removal or eradication of pathogens is up to log 5 within about 72 hours, up to 7 days. And it's basically through the algal increasing of pH, which happens when there is photosynthetic activity, and there are potential exudates that the algae actually release when they are growing or proliferating that actually create unfavorable conditions for bacterial pathogens such as E. coli to continue growing. So that is basically the mechanism. It seems to be the photosynthetic activities and an increased pH that make it difficult then for pathogens to remain viable. Looking at the NMR data, the nuclear magnetic resonance data, where we were just wanting to, resonance data, where we were just wanting to see what is the change in the compounds within the samples. But we looked at the reed bed treated sample, which is the final treated sample in the, in the conventional treatment cycle at Winery B. And we found that there was actually eradication of phenolic compounds and some biotransformation of metabolites within the effluent. So that also gave us an indication that not only are we seeing some of these parameters actually being positive, but there actually is a biotransformation occurring, or a remediation process occurring in the removal of certain compounds within the effluent. So when we looked at the paper and pulp effluent, which was actually high discharge volumes, low pH, very little, if any, retention time, we found that the algae were able to increase the pH over a 7-day period from a 4.3 to 4.7. And that also led to us realizing that there's a need for a match of the suitability of the effluent to the actual algal species that we are applying. In this case, we've only looked at the chlorella co-culture. So the color of the effluent was quite dark. So there was not a lot of light penetration. It was low pH. And so because of the complex compounds, it was a delayed process or a longer acclimatization time for the algae to actually break down more complex compounds to be able to grow. And certain effluents, such as the combined winery effluent, which has limed effluent as well as some domestic effluent, will then possibly shift the algal growth kinetics from being autotrophic, meaning photosynthesizing, and mixotrophic, where they're just literally taking up compounds. In that instance, we might find that there's an increase in, chlorophyll A, or a reduction in chlorophyll A, but an increase in biomass. So various effluents basically trigger different algal responses and metabolic processes. But the ideal is to always understand whether we reach the required water quality improvement. The effluent retention times and volumes are also important. And we make the paper and pulp effluent scenario as an example. There is no retention time. So although there's potential for algae to be applied in that space, the operating setup does not allow for that. So it would have to be a conversation in terms of, is there a pre-treatment step that can be applied, or is there a retention time, or is there some way to treat the effluent such that the retention time is increased and it's not just discharge and monitoring. So those are some of the things that would need to be considered within the industrial space. And then, for example, with Winery B, where we saw a removal of compounds and biotransformation of compounds through the NMR, the nuclear magnetic resonance testing, it also was very low in nutrients. So it was treated to a point and had very little nutrients remaining that could then support the viability or the growth of our algae. So that's something we also need to look at. So that could be applicable for the removal of emerging contaminants, but maybe the algae need not be applied at that part of the treatment chain. So possibly when after the effluent is limed, or when the effluent has been combined, the algae can then be applied then, as opposed to treating water that is slightly lower in nutrient composition, because then that leads to what we call a crash, where the algae are not receiving enough nutrients to continue. They're not able to take up any nutrients to basically sustain them. And so we have a crash in terms of the chlorophyll production and as such the biomass. So they end up dying off. So we also need to look at the various characteristics of effluent that we receive. So that is the importance of the preliminary testings that we are kind of applying in different industries. Within this, we're also in a process of signing a non-disclosure agreement, an NDA, with one of the dairy industries, and we're hoping to look at the viability of algal treatment or phycoremediation in that industry as well. So basically what the algae are able to do, they are able to bind and sequester heavy metals. They are able to break down complex pharmaceutical compounds. They are able to take up nutrients, and they are able to outcompete pathogens. So with that, they provide a very rich biofilter to bring effluent to a desired state in terms of the parameters required. The other important thing that we are also exploring, we're piloting this in the domestic space, but the idea is that we would like to close the loop, meaning when we introduce the algal biomass into the system, how do we effectively remove it and repurpose the biomass for other usage? So algal biomass has been applied in various applications, such as lipid production, energy production, and also possible applications in packaging. So in our instance, since the algae would have undergone a treatment process, we would then need to do some risk analysis for one. So how do we adequately harvest the cell biomass, and thereafter what risk assessments and analysis need to be conducted so that we can find the ultimate fitness for reuse in different industrial or domestic applications. So that is one of the things that we are continuing with, and we're using Mossel Bay because that is our ongoing pilots, just to also look at that, setting up a better or a more feasible and robust valorization method. So what is the way forward? The way forward is for us to continue increasing visibility and a network within the industrial effluent space, hence this presentation. And we're also trying to look at making it even more cost effective. So by virtue of the effluents having nutrient loads, they are able to sustain algal life. But when we mass culture, we are also looking at what other more feasible substrates can we apply so that the whole offering is as cost effective as possible. So that we are actually doing some trials there, looking at various substrate sources that we can apply so that the offering in its totality, from maintaining at pilot stage, mass culturing in the lab, and so forth, is as cost feasible as possible. And we're hoping to get an ongoing waste or substrate stream that we can continue to make use. So basically doubling up on the circular economy, closing the loop. So using waste substrates to sustain the algae, thereafter using the algae to further treat effluent, and then reusing that biomass finally for other valuable repurposing. And the idea and what we would like to do is to have a living library of algal isolates, meaning, for example, in the paper and pulp industry, perhaps algae that are more suited to a lower pH and then can perform or remediate the effluent slightly faster. And we also want to optimize how we are tapping or measuring the removal of various emerging contaminants and specific compounds. So we're looking at NMR just as a preliminary step, and then what next from there. So now that we know that there actually is some bioremediation activity from a chemical scale, not just looking at the actual chemical parameters, but actual visible compounds on the spectrum that are actually being broken down or removed, we need to then start identifying those compounds for various industrial effluents to say, within this space, within these kinds of parameters, this is what the algae is able to do, which then makes the overall offering more bankable and practical. The other thing we would have to or we are looking into is the practicalities and implementation. Considering that we've piloted this in a domestic space, what does looking at industry entail? So what infrastructure is already there that the algae can then be introduced into? So for example, there's aeration or mixing ponds in some effluent treatment infrastructure that we can already introduce the algae into, and there's already mixing efforts, which are an added plus because we've kind of tried to make it suit the most minimal energy and cost parameters or contexts. So that is where we basically are. And we're really excited. It seems to be quite interesting, and it's been it's really been fun learning about the various industrial interplays and how we can actually optimize or fine-tune the algae to continue performing in different environments. So I'll end it there. Some of the linkages and opportunities that we're looking at is within the industrial space. We've kind of broken into the domestic space. We want to get a really steady grasp on the beneficiation or reuse of the biomass in a way that is not going to have any health risks. And we also are looking into the health space because of the algal ability to remove or sequestrate certain compounds and pathogens. We want to look at the ability of that application in, the mitigation or treatment of conditions such as Guillain-Barré, since the algae are able to remove or reduce the virulence of pathogens such as Campylobacter, which are very strongly linked to Guillain-Barré, for example. So I think there's a lot of avenues to be explored, and yeah, these are the linkages and further opportunities that we are foreseeing with the current phycoremediation intervention that we have. So thank you, and I'll stop there.
Thank you very much, Leander. I think you can maybe leave your contact details up for a minute longer. I would like to ask all our participants that if you are working in a space that has effluent and you're willing to join the database of effluents that can be tested with these different algae, even if it's just at a lab space for now, but with the possibility of moving forward into pilot scales, please do reach out to Sam or to Leander. They really would like to see this research grow into a very practical implementationable option, especially in remote areas. Housekeeping quickly, we're just going to go through the chat in terms of questions first, and then I will unmute everybody. And then if we can please have raised hands for questions. Luckily, Leander's left some nice time available for questions. So we'll start with those in the chat quickly. The first one I've got here is from Gustav. I'm not sure if some of this might have been mentioned during the presentation, but given the potential for heavy metal bioaccumulation, secondary pollution from biomass decay, and eutrophication risks, what monitoring and disposal strategies would you recommend to ensure algae-based phycoremediation remains both effective and compliant in large-scale industrial applications?
Okay, so the idea of harvesting. So we know that the retention time currently in the domestic space or in the domestic effluent space is about 10 days. So then that would mean that we would need to devise a harvesting, a biomass harvesting plan that keeps in mind that we are able to basically treat in the muscle base space is about 0.2 megaliters within that time frame. So then we will continuously remove the biomass. So we shouldn't have an issue where we are having the accumulation of or the bioaccumulation of compounds such as your heavy metals, and then have the actual decay of the algae. If there's a consistent or constant influx of nutrients, that should not happen. And when there's a consistent or a planned removal strategy, so meaning how are we harvesting the biomass, that should eliminate the risk to some degree. And because we are not really, so in Mossel Bay, we're not releasing that effluent into any rivers. It's currently being used just for irrigation. And when there's contact sports at the moment, we don't use that effluent for any irrigation. So the idea is if there are now those kinds of measures in place, that should combat the risks associated with it. But it is an ongoing study and we are learning as we go. So yeah, my answers may not be conclusive at the moment, but that is just, where we are in terms of our thinking. I don't know if that answers your question at all.
Thanks, Yolanda. We'll ask Gustav to comment again when we open up mics in a little bit. There was another one here. I think some of it was answered to an extent, but maybe just to answer directly, we've got Reginald from Valterra Platinum asking, can the treatment reduce sulfates in water?
Yes, it can. And that is we would have to, again, look at the overall effluent overall effluent characteristics. So if there is enough nutrients within that effluent and it is at a reasonable pH or where the algae can actually remain viable and there is enough time for the algae to actually proliferate within that effluent, then the answer is yes.
Thank you. And the last one from the chat was, do you know if the algal mass is suitable for biochar generation?
At this point, no. I do know that it is, or we do know that those are some of the proposed applications. So we were trying to look at the most low risk in terms of, because one of the thoughts was the algae in itself prior to, being applied in a kind of a treatment can be used for, nutraceuticals, fertilizers and animal feed. But because it would have gone through this kind of a treatment process, we do realize there may be some risks, especially with the pathogen sequestration. So at this point in time, we haven't really gotten concrete applications that we know for a fact. But the more low risk in terms of human or animal feed risks and those kinds of things, that is what we're more gearing towards. But yeah, that would also have to follow a more comprehensive study.
Perfect. Thanks, Leander. I have allowed microphones for the audience. If you would just raise hands if there are any more questions for our presenters. Another one in the chat, and then we've got one hand raised. Just a comment, it would be interesting to see how often maintenance dredging would be needed to remove accumulated algal die-off.
We haven't had any die-off, interestingly, and that's because, like I mentioned, there's a constant influx. So we dose as the effluent continues. So we're trying to make sure we've got effluent constantly coming in that has no algae, and we are introducing the algae to dominate that effluent and remove nutrients. So as long as there's an influx of nutrients, and there's light, and there are all the parameters that keep the algae viable, considering that they remain viable in the natural environment in any case. So that has not been an issue because we don't have it's an ongoing, it's a continuous culture. It's not a batch culture where it's a closed environment and there's nothing coming in and going out. There's constant nutrient influx. So that is what has made this kind of viable over the years. However, when we do want to perhaps contain the biomass and then harvest it, that may be a concern. So I think it would be based on the different contexts and what is currently available and how do we implement it.
Right, a hand from the audience. Bonani?
Thanks, Bonani from Water Research Commission. Thanks, Leander. This is a very interesting study. I'm looking at the impact beyond sewage treatment plants. I'm looking at one day we solve eutrophication problem in the Alps. So Alps poor them and many others in the country. As you know, they are in trouble. Where is your study going? Are you linking this to DFSE, DWS, efforts to solve eutrophication in the country one day in terms of scale? Thank you, Chair. Thank you, Leander. Thanks for the presentation.
Okay. Thank you for the question. And yeah. Okay, so from a eutrophication standpoint, with the algal blooms, actually algal blooms from our study within the Mossel Bay context, algal blooms, specifically cyanos or microcystis, which is what I think most people would be familiar with, they normally only occur in the event that the ponds are not dosed accurately. So when the ponds are not dosed enough or the algae within the bioreactors don't receive sufficient nutrients, that is the only time that they become outcompeted. And then in the more stationary final pond effluent, then you will have, because of the stationary waters, you will then start having an increase of opportunistic cyanobacterial blooms. But for the most part, over the 9 years, so we've only had 2 incidents actually of algal blooms and unwanted or nuisance algal blooms in Mossel Bay since the implementation of this treatment. So I think that's testament to the fact that when it is well looked after and maintained, it does perform as expected. We are trying to make more linkages. I think one of the critical steps for us is to get the biomass removal or valorization, nailed down or optimized so that we can have a more complete offering, From an algal bloom perspective, we are also currently busy with other work where we found that bacteria. So the algae itself can outcompete the opportunistic algal blooms. However, in the place where there are already algal blooms and need to be mitigated, we have looked at the application of bacterial isolates that are normally just introduced at just the right ratio. So the complexity with bioremediation or bacterial based treatment of algal blooms is normally the fact that when you introduce bacterial isolates in overkill, you then contribute to the lysing of the cells. So the cells break up, the cyanobacterial cells break up, they release the toxins, they release that foul odor, the geosmin, and then the water quality actually gets worse. So in what we are trying to do, or what we've been working on for a number of years, is the introduction of the cell numbers at concentrations just right to actually diminish the bloom. So we're trying to fast track what would be a natural succession. So yeah, it's a lot of play on what concentration is currently available and what kind of blooms we have. And then from that, we are able to dose. So we've tried that at a lab scale, and we are also piloting it actually with Umgeni Utukela in KZN, because they've had hypertrophic waters for, I think, the past year now. So they're looking at something also that's low cost. So there are many avenues and connections and linkages we would love to make. And we're hoping that with the improved research that we're doing, it's obviously contingent on that in some spaces, and in some it's just making the right connections in a presentation space like this.
Bonani, I trust that answered your question. I see there were two other hands up that disappeared. Perhaps it was answered as well, but please feel free to put your hands up again if there are more questions. Another one from the chat: how would algae be removed in large-scale ponds? Has any work been done on types of technology, filters that would be suitable to remove the algae or the waste from large installations?
Okay, so we haven't done a large scale study, but again, I'm going to keep referencing Mossel Bay because that's where we're piloting a lot of this. This might sound, we're using a filtration method. So we initially looked at the use of flocculants. So for larger volumes, you would possibly look at flocculants. We looked at various flocculants such as Z-Tag that work really nicely to flock the biomass afterwards. But then in keeping in with the green thinking, we wanted to use a more filtration-based method. So believe it or not, something like muslin cloth and pantyhose work really nicely because it's just enough meshing to be able to capture, but the cells are very small. And then the challenge there is, how do we optimize the biomass yield so that there's enough biomass produced so that it can actually be repurposed for something else. So at this point in time, no, we haven't worked on very, very large volumes. We've just literally worked on maturation ponds, and we are trying to keep green. So we're trying to use the filtration meshing method as opposed to flocculants. But I think in a more larger space, then flocculants would probably be more efficient, and then harvesting biomass from there. It's just that in spaces where cost is a very critical factor that needs to be considered.
Another one from the comments section: could there be any negative DO impacts and outflows or discharge of the treatment into the rivers?
We haven't had any discharge into the rivers as yet, but from the treatments, we have gotten positive feedback from farmers that abstract groundwater downstream of pond 7, the final effluent pond. The only impacts that would occur is if there would be algal die-off. But at this point in time, if algae are viable and removed from the effluent, then we don't foresee any negative impacts, because we're not planning, or the idea is not to release algal dominated waters post the treatment space, so post the whatever set up for treatment, which is why we want the harvesting method or the valorization method to be optimized.
Fantastic, thank you. I don't see any more hands or comments. If there's any last questions or comments that anyone would like to pose to Leander. I see Bonani's got his hand up again.
Yes, I'm really enjoying this discussion, and I'm looking forward to working with CSIR and in phytoremediation projects. Like I said, if you talk to DWS, and we are starting something with University of Victoria along the same lines, but
Mm,
using plants,
mm,
macrophytes. We have
mm,
tried with macrophytes in Hatties. I'm sure everybody on this chat knows about the eutrophication problems in the country. So one is trying to say, can we have a way, because we don't have land to expand wetlands to purify water before it gets to the dam. Yes, of course, the wastewater treatment plants must do their jobs. Now, to help that situation, we are hoping that we can actually find innovation where you pull these nutrients, especially nitrates and phosphates,
mm,
out before they reach the dam. In other words, small scales of treatments
mm,
before water gets there. Because the mega approach where we put everything into a wastewater treatment plant, when it fails as they fail, then everything just goes into the dam. So I was
mm.
looking at that, Leander. One day we have a bigger scale of what you have now at labs and pilot sites. Uh, Thank you very much and all the best. Looking forward to working with you in future. Thank you.
Oh, thank you so much, Bonani. Yes, that sounds fantastic. We are, yes, definitely interested. Yeah, the algae can be used as a pre-preventative measure. In the event that a bloom has occurred and then we require mitigation, that is where the bacterial treatment I made reference to would be, more effective. And that's what we're looking at with Umgeni. But yeah, we are happy to be a part of any initiatives and also share the data and information we've gathered so far.
Thank you. Thank you, Sam and Leander, for your time. It was really very nice to see the work that's going on there. Sam, you want to close out?
Hi, Abby. So I just thank you very much, everyone, for joining today. So I just want to encourage you, if you're interested in, partaking in this research, we are looking for different effluent from various industries to test with our algae bioremediation methodologies. So I'd encourage you to either drop us an email, if you can give us some indication onto what type of effluent management systems you are interested in exploring, what sort of characteristics of the effluent streams in terms of the COD, nutrients, retention times. That information would be very useful. Alternatively, I'm also just going to quickly drop a Microsoft form into the chat box, which you're welcome to fill out. And that will also just indicate whether or not you're interested for us to contact you to see if there's any avenues for exploring this with you and your industries further. Thanks, Abby.
Thank you very much, Sam, and thank you for all our attendees who took the time to listen to Sam, Leander, and be part of understanding the changes that are coming in our society and how we can work together to achieve more. So again, thank you very much. If there's nothing further, I'm going to close the event. Have a fantastic day, everybody. Goodbye.